Hi, everybody. Hey, thank you for coming to play. This is probably going to be the most exciting presentation I've ever done in my life because I succeeded in breaking my laptop since I've been here. The motherboard is cracked, which means if I touch it, it powers off. So I spent about 15 minutes just before this talk just manipulating the case till it powered on. And now it has, so let's give it a shot and see what we can do. So x equals x plus 1, except when it doesn't. So firstly, me, hi, Team Periwinkle, red team, blue team, kind of a nice shade of purple. I work and do what?
Generally all out sexy beast.
Oh, I try, yes, all out sexy beast, thank you. I work Holy Wars, tabs over spaces, VI over Emacs, although I'm starting to soften towards Space Max, which is VI plus Emacs, but that's another story. And I would prefer any kind of root canal over System D. Sorry, I'm old school. Not going to apologize, except I just did. No, screw it. I'm a rapid slide addict. I have 85 slides in this presentation. Traditionally, it's meant to be 3 minutes a slide. I have 60 minutes, so I've got to hit one slide every less than a minute. And I've already used 3. So we're ready to go? Someone's going to have to tell me when I'm close. Here we go. 3, 2, 1, go. Okay. Solve for x. Anyone remember algebra from high school or wherever you did it? So if x equals y plus 1 and y equals 1, what does x equal? 2. That's right. Confidence. Yes. And if y equals 2, what does x equal? 3. Yes. So solve that. If x equals x plus 1, what is x? Well, you can't. That's the problem. So why can't you solve it, and why the hell am I making you care about this? Well, all will become clear. So I want to live forever, like Lady Cassandra. Really, I also want my code to run forever, but that's really, really, really hard to do. I want to scale forever as well. The problem with scaling is this wonderful, gorgeous flat line right here. That flat line is Moore's law. It means that it is when Moore's law broke down, is a more accurate statement. Since about 2010-ish, the speed of CPUs has flattened completely, yet the number of transistors has gone up. We're hitting physics, and as of right now, we can't break physics. So I can't buy a faster CPU, but I can buy more of them. More CPUs, good. The problem we have is that the software industry is decades behind this. I think you remember when you got your first ever, 2 or 4 core processor, and you tried to render video, and you were like, yes, I'm using 100% of one single core. Oh, yeah. So we're so far behind on the software side, it isn't even true. Decades, which is why I smell opportunity. Yes, it's opportunity I smell on the second day of the con, not other things. Sweet. So let's talk about scaling. Scaling 101. Vertical scaling is the concept that you throw a faster CPU at it and more memory. No, not going to happen. So what we have to do is we have to scale horizontally. So that means scaling our applications across multiple CPUs or across multiple systems. Okay, sounds easy enough, right? The problem is that the only part of the computing industry that has really got this right is the GPU industry. I mean, you can look at GPUs with thousands of cores now. Nobody else, no other part of the industry is doing that except Bitcoin, which of course is still GPUs, and data processors, which is still GPUs, but it's still GPUs. They're the only ones that have solved it. So why? Well, good question. It's because we cheated. We bought ourselves time, just like we did with the processors getting faster. We became lazy as programmers. We didn't need to optimize because we could wait 6 months and get a faster processor. So we're lazy. So now, when you look at this, the only way to really scale these is to actually put hypervisors, because that's really the only type of software that will actually effectively use that number of cores. And now we run 32 copies of our application, which makes no sense. Not only is that a management nightmare, but you're also now providing resources for 32 instances of an operating system, as well as trying to patch it, maintain it, and it makes no sense. Why can't my app just run across 32 CPUs, or 128 CPUs, or 1,024, or 10,000? Why? What is stopping us? Well, let's go into a little bit of how the systems work. So All our hardware's at the bottom. The kernel is responsible for basically providing access to and from the hardware. So the kernel does all of that. It manages the resources. And then historically, a process is a single thread, a single straight line of code. And then when you execute it, the kernel will give it a range of memory and say, this is all yours, go play. And then the kernel will make sure that processes don't stamp on other processes. And that's actually done in hardware using what's called an MMU, a memory management unit. So then we're like, well, that's really hard because now we've got software. And let's say, for example, you take some of the really early web browsers where you'd go to a URL and the DNS for the website would actually take like 10 seconds to resolve. You could drag that little window across and nothing would update it. You could draw all kinds of pretty patterns and it was horrible. So now they have threads where you can now have special types of processes which do run at the same time, and they share the same memory, so I can now have hundreds of threads doing all my work, and they're all reading and writing to the same memory space, and it's all awesome. Except it's really hard. So how do you know when one thread is actually finished reading or writing to what you need? And when I finish doing my stuff, how do I notify or know what other thread needs my data? And how do I know that another thread hasn't crashed and corrupted the data that I'm using, or just like buffer overflow in one thread might end up writing into my memory area, and this is just a single-threaded process. We haven't even looked over multiple machines, and we can't even get this right. And not to mention thread abuse on Windows. A process with appropriate privileges can start a running thread in any arbitrary process, which means, LSA, which is the process that does auth on the Windows system, I can start a running thread into that process, and I can now read that memory. Yeah, not a great memory model there, Microsoft, sorry. So we solved the problem. We used locks, semaphores, and mutexes. Mutexes is, I'm safe because I'm telling everyone else to go to sleep. Well, is that really scaling? Is that really doing things in parallel? No. All you're doing is you're telling everyone else to stop working, so it's still only one thread of execution. You have semaphores where you basically say no more than three threads are allowed to do stuff in here, so you can kind of control what's going on. But still, you still have that same problem of making sure people don't stomp all over each other. And then, of course, you have a lock, which is something that people individually manage, where they say, I have this bit of memory, thou shalt not touch, and then the kernel will actually stop other threads from touching it. So we've solved all our problems. And since we also want to do this memory sharing across processes, we've got System 5 IPC, so we can do that. And between machines on VMs, well, now we've got hypervisors that will actually let us share memory between virtual machines, which is awesome, because I can now read memory from arbitrary machines with bad credentials. And then for physical hosts, you can buy dedicated hardware, which will map memory from one machine to another. So it actually looks to the hardware as memory, but really it's all going backwards and forwards over the network. So we have solved all of our scaling problems because we have shared all of the things. Our developers suck. In C, how many different types of memory bugs have we seen in C? So we've got null pointer deref, reuse, we've got people not initializing memory before they use it. There's just classes of this. And C programmers, as a whole, they can't even manage their own diaper. They can't even manage their own memory. Well, what about Java? Well, Java protects the programmer from the dirty job of managing their own memory, but what it does is when it just keeps allocating memory till it gets to a point, and then it says, I need more memory. So it stops everyone and then does cleanup. Basically, goes through, oh yeah, not using this anymore, not using this anymore. I have seen systems, I've seen applications freeze for 50 to 60 seconds. The entire world stops. So any database connections you've got running, pause, timeout. Any people who are connecting to it, any customers, yeah, done. It's completely unpredictable. It's not awesome. JavaScript. JavaScript, they didn't even trust with threads. I mean, Node.js, which does asynchronous stuff, it's still single-threaded at its core, and they're doing it in other different ways. JavaScript, terrifying. Python, Ruby, they protect the user from hurting themselves because they only let one thread actually execute at a time. Lua just says, no, I'm not even going to try. JRuby is on Java, so again, forget it. Perl is like, I'm sorry, yeah, we did something. It's sort of compiled, it worked on maybe 3 platforms, and then it all blew up in our face. And Perl 6 was still waiting to be delivered. So everything is awesome, everything's unsolved. Any questions? No, that's really not it. So let's talk about how do we actually solve this. So right now, we are all very solidly in the trough of disillusionment. Everyone except for computer science researchers, because there's a lot of money being pumped into universities to try and solve this problem at a compiler level. They know it can't be done there, but hey, it's money. So let's talk about GPUs. So right now, March 2015, it isn't March, but it's close enough. 3,072 cores, 12 gig of RAM, $1,000 on a graphics card. Awesome. And they use it all. How awesome is that? So how are they still able to scale? Well, it comes back to this, our little friend here. Or more accurately, it comes back to not this. Because this is what is causing us our problems. The Lambert calculus. So in the 1930s, when computer theory was actually, a good 20, 30 years before actual computers, Alonzo Church invented Lambert calculus. It's a, quote, formal system for mathematical logic expressing computation, function abstraction, blah, 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 blah. Don't really need to get all of that. Just know how old this is. This problem was addressed in the 1930s for different reasons, but it was still actually addressed. But when you start to use that, you get some really interesting properties. So one of the first things we do to make our lives easier is we say we have immutable data, meaning if we set a variable, we are not allowed to change it again. Now that sounds completely strange to anyone who has done any kind of imperative or OO programming, but it works. So when you set a variable, that's it, it's done. Well, what does that mean? That now means that if you write it to shared memory, you never have to worry about anyone modifying it, and nobody needs to worry about whether you've finished modifying it or not because you're never going to change it. So it's there, it's done. So you don't have to worry about locks, semaphores, which means it's fast. You also have composition and mathematical certainty, which I will cover in a moment. So like I said, immutable data, it can live in shared memory, and you can optimize like you would not believe. So here's an example. This is, if you set let me not to the marriage of true minds into X, and then say X equals X plus teach Java, the way that it's actually implemented in an imperative language is, okay, let's allocate some memory. Let's copy let me not to the marriage of true minds to that new bit of memory. Let's append teach Java, and then let's mark the old X as being available for garbage collection, which means it can be removed at some point in the future. That's a lot of work. On the functional side, we just say this. We don't need to store a second copy of let me not to the marriage of true minds because it never changes. How cool is that? That means I can have a binary blob of like 2 gig in size, and I can modify bits and pieces of it and never need to make a copy. Oh, because when you make these guarantees, you can cheat. Composition. Composition is the idea that you can take functions and you can almost rearrange them like you rearrange algebra in math. In fact, that's effectively what Lambert calculus is. So in my example here, I've created a function called reject beer, and all it does is it says run the command get all beers, which just streams out a list of all the beers that I have, and then for every beer it receives, it runs the function isDomestic, which says, is it domestic or not? And if it is domestic, it rejects it. And then the bottom one just says, take the first 3. Now, even if you don't know what language that is, you can probably kind of work out what that means, because it kind of makes sense. Especially if you come from like a Unix background and you know what a Unix pipe looks like. It's just like that. It's cat all beers, pipe direct minus v domestic, pipe head dash 3. I mean, it's just, once you make that switch, it's a lot easier to do. Of course, the equivalent in an imperative language would have loops and counts, and you have an internal count as to whether I have a total of 3 or not yet, and it would just get messy. But remember, domestic is just a function, so what if you don't want lager? Well, if you were writing in another language, you'd probably have to write another function which looked almost exactly the same, right? Well, in a functional language and composition, what you can do is you can actually pass the function to create a function. It's weird, I know. But what it means is that I can say beer select is beer select, and then the variable for that. So the function that I provide goes into is hated, and then it's actually inside our function here, which means that my previous function just looks like this. Hipster equals beer select is domestic. How cool is that? Or beer select is lager. Or you don't even need to actually have one in there. You can actually write your function inside the function. It's just like beer select, function beer, if the price is more than $2. It's another way of thinking, but when you make that switch, it's actually a lot easier to work with. And then lastly on this topic, mathematical certainty. There are these things called monads, which are legendary because they're just a monoid in the category of endofunctors of X with a product X replaced by a composition of endofunctors and units set by the identity endofunctor, which makes no sense to me at all. I mean, so example. This is from in JavaScript. One of the most common errors that you'll see is undefined is not a function, because people will be passing functions around, and if they can't get a lookup on something, they will pass undefined, and then JavaScript will be like, okay, now I've got to execute this method on undefined, and it's like, oh, undefined is not a function, and then your JavaScript program has to go, okay, where was that defined? Okay, what was put in? And it just becomes really, really difficult. If the idea of a monoid is that you specify what it is, and so in this case, you say that the variable x is a maybe function, which means it's either a function or it isn't, meaning it's a function or it's nothing. So if you in your code have not actually written code to say if it's nothing, do this, it will not even compile. So that will just cut dead those runtime errors. So have we reached programming paradise? No. We still have side effects. One of the principles is that when you run any function with a value, you will always get the same value. This is why GPUs are so effective, because all of the individual computations are all independent, which means that you can just say, if I put 3 into this function, I'm always going to get 7. And it doesn't matter what CPU it's running on, and it doesn't matter where the data came from, you'll always get the same value out as if you put the same value in. That doesn't work when you're doing things like reading and writing to a database, because at that point, you no longer have control. So we can't avoid that. The only thing we can do is isolate them, and that's really a lot of what these other languages I'm about to talk about do. They basically say, all that nasty, impure stuff where bugs live, that can all live over there. So the example I gave a moment ago is a language called Elm, which compiles down to JavaScript. And so it has the most polite compiler in the world. So here's an example. So what happens is in this list, all of the items in the list are meant to be the exact same type. That's a rule, that's a law. It stops you doing things like, calling things as functions, which aren't functions. And it's the compiler basically says, excuse me, I'm really sorry to bother you, but I've looked at your code and, we might have a little issue here. I was kind of expecting to see HTML in this array, and you kind of sort of put a string in there. So if you could maybe fix that before I let you do a damn thing more, then that'd be great. So when you have that level of strictness in your compiler, you have no bugs. let me rephrase that. You have very, very few runtime bugs in your actual running code, and that's what you want, right? You want to catch it before you deploy it and before your users see it and before it, modifies stuff. So, for the backend server side, this is my personal preference. So the Beam is a virtual machine that is 28 years old. And then there are many languages that run on it, but the two that I'm going to focus on will be Erlang and Elixir. And Elixir is 3 years old. You can run millions of processes inside this virtual machine. Now, it's not an operating system process. It's a process which is specific to this virtual machine. And I can spawn up millions of them in seconds, like it's nothing. And they only take up about 500 or so bytes just to manage a single one of those. This environment was built from the ground up, I'm just going to point out, 20-something years ago, to be fault tolerant, to the point where you can actually do editing and running of code while your application is running, while you have live connections. And the reason for that is because this never happened. You have never received a phone call from the phone company or a letter from the phone company saying, between 3 a.m. and 6 a.m., please don't dial 911. Because we're upgrading our switches. That never happens. And the reason that never happens is because right at the very beginning when this stuff was built, and computer science was actually real engineering and not, people cutting and pasting stuff off Google. They really cared about that because if they got it wrong, people died, and death matters. So, two sides of the same coin. They are 100% interoperable. They both compile down to the exact same bytecode. Erlang is Prolog syntax, which I have a hard time with. The tooling is likewise a little on the old side. And the development team for the VM and the language are incredibly conservative. And the reason that they are incredibly conservative is because they don't want people to die. To the point where they will do a release every 6 months, every 3 months, 4 months, 6 months. There's no rushing. There's no, hey, it'd be cool if. It is, everything is incredibly well done and engineered. It is insane. Elixir's the little looser child, and what it does is it has a Ruby-esque syntax. It has far more modern tooling, which is more pleasant to work with. The additional libraries is really what I'm referring to when I say it's a little looser. So their development is a lot more cutting edge, and the language also gives you the ability to create your own languages, which is cool. So if you've got a specific job you want to do, you can actually generate your own computer language that will actually work that. So your program actually looks like a description of what your app needs to do. It's pretty awesome. Performance-wise, here's an output from a server at WhatsApp. This is about 2 or 3 years ago. This server, single server, one machine, I think it's 16 cores. It's a fair amount of memory, though, in fairness. 2.2 million concurrent connections. That's not 2.2 million people, connecting like, transient things. No, that is solid TCP connections, 2 million of them established right there, right then. And the thing wasn't breaking a sweat. The model for this is so right, and they had to get it right, because if they didn't get it right, people died. WhatsApp itself, so they had 450 million customers at the time that they actually sold it, sold for $19 billion. It was built by 35 engineers. Just think, when you think about, when you see these huge development houses, with hundreds of developers, and it's like this application was written by 35 people, and it handles, 450 million people, almost 500 billion messages a day. And it's just a little bit on the mind-blowing side. And unlike Twitter, no fail whale. I mean, their availability is top. It has to be, because people assume it's like the telephone because they're using it on their telephone. The philosophy, that's difficult to see. The philosophy in in Erlang and this type of software is let it crash. The processes are completely isolated, which means if a process over here crashes, it cannot hurt anything else. It's designed like that. And these processes were designed to live across multiple machines, which means if you have a machine fail, or your network splits, or memory dies, anything like that, this is already taken care of for you. When you write software and you're doing, you're a good software developer, and you're like, okay, so I just ran this, I need to check the return code to make sure it was successful. Okay, it wasn't successful. As a programmer, have you ever enumerated every single one of those failure conditions? It's just not possible. I mean, you can't say if the CPU died in the middle of this transaction. You can't do that. The language itself does this. So if you kill something, or it kills itself, the process just above it, which is in blue, is called a supervisor. It restarts it with the exact same arguments as before, which means it does the same thing again. You don't even need to code that. So I think it's like 30%, 20%, 30% of failures, software failures. If you run the same thing a second time will work. So it's things like network timeouts and that kind of stuff. Done automatically. I don't even need to test for that. I've written stuff that reaches out to remote APIs, and they've sent me back a 400 saying we're busy, try again later. That's okay. I don't even need to take care of it. My process goes, that's not a 200. I'm going to die. Boom. Starts up another one, makes the same request, gets a 200. Okay, I'm done. How cool is that? I don't even need to worry about it. I don't need to go, okay, maximum of 10 times, wait 3. I don't need to do any of that. It just happens. And when I spawn, if I need to do 10,000 requests, I'll spawn 10,000 processes. I don't care. Why would I not? I don't have to manage it. This manages it for me. In fact, if you actually error trap in your code, it's considered an anti-pattern. The only thing you really code when you do this, when you actually use this, is stuff like the user types something in wrong and you really want to feed it back. That's about it. Anything else, just let it crash. Let it crash as quickly as possible. Let it die as quickly as possible so it doesn't hurt anything else. Boom, done. And the environment is designed for failure because that's pretty much the only certainty we actually have in life, is that our software will fail. And you can look at applications that I've written, and you can watch the debug logs, and I'll see process crash, process crash, process crash, process crash, whatever. No one knows, no one cares, because it's natural, it's normal. It's completely normal. I am not scared of crashes. It's very liberating. One of the original switches, what this was originally designed for, back in 1985. 1987, it was released to the world. 1985 was when this all started. They were getting 9 nines of availability. They were getting 31 milliseconds of downtime per year, and they were not having maintenance. This isn't, oh, well, they also take they also take an hour every month. No, it's a telephone switch. They can't do that. This is, okay, we need to do some code upgrades. Okay, then we need to actually do a hot code upgrade. We need to do debugging. Well, we can't stop it and turn on a debugging flag. We need to debug it live. How do you debug something when you've got 1 million processes and you need to debug one? How do you do that in any environment if you cannot interact live with it? You can't do what you do in most languages, which is, okay, I'm going to run the version again, but with the debug flag on, and then it creates debug for the other 1 million processes. No, you can't do that because you lose everything. This is thought about and engineered right. And it's a happy accident. When it came to scalability, this is a happy accident. They weren't thinking multiple CPUs. They were never thinking 10,000 cores. There were telephone switches on the end of lines. They could not do shared memory because they could not copy memory backwards and forwards because there wasn't enough bandwidth. So they never implemented it, which meant that this entire model works because of this. And the models that you need for actually building these servers, they already exist. GenServer is a generic server. GenFSM is a generic finite state machine. GenEvent is a generic, if I receive event, who do I send those events to? GenTCP, I have received a TCP connection. GenUDP, I have received a UDP connection. Writing these protocols is as simple as just, I receive a message, I send it. I receive a message, I send it, regardless of what it is. This is all about, it's almost like just playing mail. It's a lot of fun. The point that I'm making, though, is that we've gone a long way in the direction that we've gone. And to really succeed in the future, we need to go back to the past and fix a lot of the mistakes we've made. And I think that this is destiny. I swear to you, I have not photoshopped this. I swear to you. 1985. It's 1985 to 1987 when Erlang basically was first invented. 2012, when Elixir was first released. 2015, October 21st. Well, we're 3 days late. But can we change the world, please? Thank you. How much time do I have?
Well, a good bit. You get like 20 minutes. You started late.
Oh, I can do some demos if you like.
Yeah, let's do that. And
okay. Tell you what, let's do questions first. So.
Yeah, no, I'm so programmers in the room? Programmers, no? I'm curious, I just have been dealing with, at work, a challenge of using some of these languages, like when you talk about, don't worry about this crash condition or don't worry about this or whatever, how some of that obscures their knowledge of some of the underlying protocols and other things that are actually going on, and like you mentioned, TCP timeouts and all those types of things. Mm-hmm. And while it's great to not capture those things necessarily because they are expected, mm-hmm. And to recover from them, it is also very helpful, though, for them to know how that stuff actually works.
Sure. And
for some reason, I've found that as developers are coming up, they're not familiar with these things. So I'm just curious because I know the spirit with which you're talking about it, mm-hmm. knowing that the detail of that very well, for other developers or other people in the room that are dealing with those that are less knowledgeable about. Mm-hmm. Any feedback or any input on how to?
So it's really a matter of context and control. Excuse me. So with the supervisors, they don't actually retry forever. It's configurable. So for example, if you're trying to write to a database, and the database write fails, you kill the child, and it'll try to execute that child again. If it's because the database is down, then it's going to fail again, and 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 again. Is that helpful? Probably not. So what we do instead is this. If I go back to our diagram. So what we do is right here, let's just pretend that, this is our worker here which is having a bad day, right? This, and then this supervisor right here, let's just say that it's basically been set to say, if it crashes 3 times within a minute, then don't restart it. What will actually happen is this, again, configurable, is that this supervisor will optionally kill all of the other children underneath it and kill itself. And then this supervisor will restart this supervisor, which will restart all of the children, which means that you now have the ability at this level to say, okay, my entire database pool crashed because something bad is going on down here, don't know what it is. Therefore, I want you to restart this supervisor, but connect to this pool instead. Make sense? So it's self-healing. The errors, you still, you can see.
By that you mean like the idea that if I need to ensure message integrity or kind of the way that I think about it in terms of a database mm-hmm. is you want immutability, right? So that's obviously losing data or something like that would be bad. Or in the context in which you're discussing this would not be a good solution for that. I'm just curious.
Well, so it all comes down to the domain of your problem. So let me give you an example. So there is a ad delivery. There's a company that does ad delivery, and they use Elixir on the back end to do that. What happens is There's basically a marketplace, almost like a stock exchange, where someone will hit a website, and then that website will send to the exchange, I have this user who's interested in these things. How much are you going to pay me to display your ad? And there is a real-time bidding process on your eyes. And they actually have an SLA of they have to respond within 4 milliseconds or something like that. I know you're choking at the thought of this, right? So here's a question: does it matter if they lose? Does it matter if they lose data or if they lose availability? Probably not in that case. So so in their case,
well, especially not in that response time, because
right.
In that, but I'm thinking things like for security applications or something like that, or audit logging or something like that, where I've got high volumes of messages that need to be stored and transferred, where underlying responsibilities of TCP or reliable network delivery may not be adequate enough.
So there is so a good example then of that kind of thing is if you take eJabberD, which is the messaging server, which is written in Erlang. They actually spawn a new process for every message. And the reason they do that, I know it's crazy. So what happens is, if you think about it this way, say I was going to send a message to you, my users just said, send this message over there to Evan. I'm like, okay, so I'm now throwing them, if we're doing it, but it's just me and you, and I can't reach you, then I'm going to be sitting here going, hello, hello, I have no idea what's going on, hello, hello, and ignoring my user over here, right? The way eJabberD does it is they will say, I'll receive the message, and I'll be like, sure, that's a great idea, here you go. And I generate a process. And that process basically then runs and says, I'm going to go and find Evan. And if it fails to find Evan, it will crash and notify me that I couldn't be reached. So what you can do is you can have processes. I'm showing these directly, but any process is actually capable of monitoring any other process, which means that it will get notified if that process dies or exits, which means that if I spawn 10,000 jobs, I can actually say, let me know if any of them fail. And then I can make a decision as to whether that's important or not, or I can get a supervisor to do it for me, and then it just says 10,000 is good or bad, and then, does that make sense? So it really is, it's all about the problem you're trying to solve, and it's not, this doesn't limit you into how you approach it, because there are actually ways of doing it, solving each of these problems. So you don't have to choose once per app. You can take every use case you have. With logging, for statistics, we may not care if we lose one. For logging for security, okay, we're going to make sure that is never lost, which means, oh, that process crashed. Okay, I'm going to write it to my local disk. Do you see what I'm saying?
So I get what you're saying. Yeah. The aspect is you have to think about the context of your application and what you should do with that data to create failure scenarios, pretty much. That would be kind of almost like what you were talking about before, where, like in the failure scenario case, where, okay, I don't care, so I throw the data away. But in that instance, or where you were talking about error handling, I guess, where it was actually I can't remember what the slide was that you had where it was on error handling, how it was actually like an exception or something like that. Like if you tried to write the code for certain failure scenarios or something like that.
So that is that is Elm here.
I gotcha. So it would be kind of like that would be the error scenario that you would write to, not necessarily how the service or how application level it would respond, I guess. Does that make sense? Or?
Well, this is actually at the compilation level. It will not even let you generate code because it knows that what you produce will be broken. Okay. So it knows that what you produce will be broken, therefore it doesn't produce it until you fix it, which as a developer is really what you want. I mean, in theory, that's what tests are meant to be for, right? Our regression tests and unit tests. These tests are meant to be all about let's make sure I didn't do anything stupid, like, stick a floating point number in where it's expecting an integer and make sure it doesn't crash everything. This kind of stuff will be caught automatically by languages like this because they explicitly disallow this type of activity. Although, disclaimer, Erlang will let you do that, and I'll tell you why. So, remember I said you can do hot code loading? I mean it. So, for example, if I have an IRC server. I'm running an IRC server, and I have 500 connections open to users, and users are chatting away and whatever, and I need to change the code in some way. Let's say I need to change, I need to add some other field to, to what I'm storing for a user. And so instead of, storing the user as a field, with these other things, I'm now going to add a new one. Well, I'm now changing that type of data, right? So when you do a code release in Erlang, again, when I say Erlang, you can just mean any language that runs on that platform. You can generate, when you generate your release, it will go, what it does is it goes up, all of these servers work on messages. So they sit there doing nothing until they receive a message. So for example, with an IRC server, it may be, I received a message on this TCP port, it's this, it would go parse, 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 do this, send a message. So there is a special message called code reload. And then what happens is when it receives that message, it will go ahead and reload the code into that specific process, which means that you have to like loosen those chains a little bit so you can do things like change data types. But then when you push the release, part of your release is, I'm changing this code, I'm also changing this data type. All these users which are in flight make the default for this, and it would actually load in the new code, modify the data actually in the, in the 500 running processes to be the new format, and everything will just continue. It is just the craziest thing.
Well, and that I don't know, is everybody following kind of the conversation we're having here? I know some people that are not as development oriented may be a little bit confused, but so what he's essentially saying, and what's so cool about this, and one of the things where some of these languages become really popular, so and why it's important to you as a security person or a tester or whatever, is that, so like now, when you change this C, or like in C language, anybody? Come on, nobody? Okay, how many of you have written a script? Okay, so what happens when you start a script and you need to change something? You have to kill the process and restart it. You have to respawn it for the changes that you made to take effect. And so a lot of C applications are that way as well, or, but the idea of this is that dynamically, because it's launching these things for each individual action instead of processing them in serial, for lack of a better way to describe it. I mean, instead of processing them in serial based off of a single process, it may multi-thread or whatever, but each time it's loading that code base back up, and when you set that flag, it simply tells the process when it spawns that I need to make sure that I pull in the latest version of this code into memory versus what it was trying to use before. So it's the idea is like really cool, where you can like open up a new port on something and not have to restart the server itself or the process that that's running it or launching it, which is really, 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 really important for real-time applications, and so that's why a lot of these are getting more noticed. But a lot of them have the way that magic under the skirt works there is you lose some of the stuff that we were talking about before, and that was why I was curious, like some of those underlying things that are there kind of become obscured from you a little bit, I guess.
You can still see them. You just choose whether you want to see them or not. So there's there's a logging application. And then that logging application, you can then choose what you want to do with it. The thing about the Beam is that the VM was originally designed to run on hardware. It was never designed to run on an operating system. So it was an embedded OS, which means it has its own applications, it has its own concept of init, it has its own concept of all of that. So you can think of it more like an OS than an actual, than an app. And so you could do things like start and stop applications. You can actually have dependencies of applications, which means, for example, there's an SSL application for doing SSL processing and certificate validation and caching and all of that. And so I have to start that before I make a HTTPS request, because I need that service in order to do that. It's really freaking cool. I am so excited about all the cool stuff I've been doing this. I've been doing crazy, crazy stuff with it. Like scanning an entire class A for SSL certs and doing SSL validation against them. It took me maybe a minute and a half to scan an entire /8. It took about 20 minutes for AT&T to send me a shittogram.
How many cores did you do that with, or how much?
That was on this laptop.
Oh,
Yeah. And the way that I did it was I just spawned a whole bunch of processes. And I just said, I'm throwing the process out into the VM. You guys do what you got to do. And so any process that reached out and got like a timeout, those processes would stay longer, obviously. And then they would die because they didn't successfully pull a cert. And then as a process got a cert, it would then send it to another pool of processes, which would then do the cert decoding. So this is all about sending messages. So it's the coolest thing. When I'm writing software now, I have a whiteboard and I have Post-it notes. And all I'm doing is I'm writing down the name of the little process server that I'm going to write. And it's like dunk, 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 dunk. I put them up and I just draw the messages that these things are going to be sending to each other. And I can map. And because of that, it's so much easier now. It was really difficult to start with. It is a completely different way of thinking. I can now map the behavior of my application at a much higher level and not worry about the fiddly little details. And then that's it. It's just so much easier to rationalize.
Yeah, because it goes back to what we were talking about a minute ago, where you have to do it in serial, where you have to, before you can pass something off to the next, part of the logic chain, you have to validate or do something that is going to prevent data or assumptions that you made from breaking, which will then break the entire chain, and usually by default, whatever it is that you're coding, even in shell or whatever. Mm-hmm. Am I going crazy here?
No, you're right.
Okay, but the idea being like in essence, the logic is the same, but how you handle it or what happens to that data, you don't have to validate it before you can write the next stage of things. It kind of opens up a little bit because it's just going to fail. Right. Instead of having to write the error scenarios before passing it to the next process, you just say, this is what it, if you work, then continue.
So the best way to demonstrate that is to show you. So hang on.
More or less by default, what you don't tell it to do, like what's not there, is a failure scenario, and it just...
Yeah. So... So I am happy to sit down with anyone who wants to sit down and learn or work out how this would actually work with one of their apps. I'm happy to sit down and, you can give me your description of your application, and I will draw on a piece of paper how I would build it and show you how it works. I'm happy to sit down with anyone and do that because, honestly, this is so. Oh my gosh, it has made such a difference to how I'm coding. So this is going to be an Elixir, which is is that big enough that you guys can see? It looks big enough. Okay. So this is an Elixir, which is the more modern language. Full disclaimer: I looked at Erlang 4 years ago or so. I bought all 3 books on it because I bought the first book, got about 2 chapters in, got stuck, gave up. Bought the next book. Again, same thing with the third book. And then I just went from book to book to book to book until eventually I just gave up. The reason for that is because I'm dumb. Because I was battling 2 issues. Issue number 1 is it was a completely different way of approaching problems, like a completely different way of approaching and solving problems. So you've got that huge thing to get over. And the second one is I had a real hard time with the syntax. The syntax is Prolog. And for the people that use it and run it, the syntax is actually really, really, really simple, but when I look at it, it just did not make any sense to me at all. What Elixir did for me was it had a syntax that was easier for me to grok because it was more like languages that I'd seen before, which then meant that attacking the problem of understanding how to build apps and how to structure them all was then an easier thing. Now I can do that, going back to Elixir going back to Erlang and learning the syntax is actually not difficult at all. So, what was I going to show? I lost my train of thought. An example of?
Simple app. Hello World.
Hello World, okay. 1,000 times. So Elixir has a build system called Mix, and I'm going to create an app called Hello SDC because. let me make this slightly easier on myself. So I'm going to pass the arguments sup, which means supervisor. So it's actually going to give me a full application. And, it comes automatically with tests and all that other good stuff. So, oops, mix, test. There you go. So, it's got one test right now, and, you're meant to do all the right things. So, you know what? I'm not going to show that because that's going to be hell. Let me shrink this. So I remember what I was going to show. This is going to be, oops, no, I want to zoom out. I'm going to try and, I need a little bit of width, which is the only reason I'm doing this, so hopefully that'll be good. So I'm going to create well, first of all, I'm going to start tmugs. So I'm going to create a library, and so it's going to be, functions in Elixir and Erlang live in modules, so I'm just going to go ahead, and they're hierarchical like they are in, many other languages. So I'm just going to go ahead and create one here. So hello SDC, and I'm just going to call it world. Okay, so def module does exactly what you'd expect. So this is going to be hello SDC dot, what did I call it, world? Okay, fine. And so that module, in theory, now exists, right? So I'm going to use one of the things that we talked about before, one of the generic solutions. We're going to use what's called gen server, which is going to create a server. And then I'm going to specify how to start it. So I'm going to start it with no arguments. And this is just something that, what I'm typing in now is something that you'll do 1,000 times, so don't stress it. Of course, since I said I'm going to do it 1,000 times, then of course that means it's going to have syntax errors all over it. Oops, and then def init nil do, and I'm just going to make it print out a logger which says logger.debug hello world. Okay. This is when, because we're doing demos, it's going to fail to compile. Okay. So let me go ahead and start it. Oh, it did. Okay. So I'm going to go ahead and start my process. So to start my process, it is, I've forgotten what it's called already. It's hello SDC world start link. Oh, bad return value. Oh yes, that'll do it. So what happens is I have to return what is called a state, and right now, because of all I'm doing is printing something, I'm just not really going to return anything. So to demonstrate, I'm just going to go ahead and recompile my module and load it back in. Notice I did not restart my virtual machine. All I did was R for reload, and then it went ahead and reloaded the module and told me straight away. And oh, there you go, it's running. Okay, so my server is now running. So right now, all it says is PID. Okay, so that is the process ID for that specific process. And to actually show you, what it looks like, you can actually watch the virtual machine running in real time. So you can watch its load in real time. And when you've got a cluster of these, you can just go from node to node. So you've got load charts. You can look at the memory allocation and how all your memory is actually taken care of. The applications that are actually running. So here's my application, so hello SDC. And then this is the logging application, which of course I'm going to be sending logs to in a moment, and the build one, and then this is my actual shell. This is the process table for inside the virtual machine, so you can see all of the processes that are running. This is like a built-in internal database, so I can examine the database again in real time and also modify it. And then I can do tracing of individual processes here just to, keep things sharp. So let's go ahead and actually give this thing something to do. So what I'm going to do is I'm going to set up a handler for if I receive a message to this. So this is called handle cast. And what I'm going to say is if I receive hello as a message, yeah, and then this is going to be state. We can talk about that after. I can make it say, debug, I can just say received hello. And then just no reply. State. I know this looks foreign, please. It takes some work. So what I'm going to do now, first of all, let me show you what happens if you do it wrong, right? So I have not updated my code, but I do need the PID of that. And you see, I got the PID here, number 2. So I'm just going to go ahead and grab the PID. PID equals, it was the value I had in number 2. And so PID should be that, okay. So if I do, so Gen Server Cast sends a message to this process ID, and the message is going to be hello. When I do this, it'll crash. Boom. It crashes because it doesn't know what to do with a hello, because we haven't, it still has the old version of code and doesn't know what to do with it. So the process is now dead, right? So it's dead, it's done. So if I go ahead and reload the code with my new stuff, with the edits that I just made, hello, STC world, oops, there, what did I do? Oh, I see what I did, sorry. So if I go ahead and reload my module like that, and I go ahead and start it up again, so if I go, here it is. And if I go ahead and grab that PID one more time, and if I now send a message, please don't crash. Dunk, there you go. Do you see I modified the code in running memory, basically did that and done. And I can generate as many of these as I like. So for example, if I wanted to generate 10,000 of these specific servers, I can just do it like this. I can say, oops, range new, and I'm just going to do 1 to 10,000. 1 to 10,000. Okay. And like I said, this works like Unix pipes. So it means every time that I do this, so enum.map basically means run this function on every value, which means it's going to run whatever I put in now 10,000 times. So I'm going to say, I want you to run 10,000 times for me. Oops, what is it called? It is called hello. This is really nerve-wracking doing live coding. Hello SDC dot world /1. Please. Nope. What did I do? Mod fun. Oh, I see. I forgot the name of the function. Start link. 10,000 processes. Nope. Come on. Where are you going? Hello. Start link. Oh. Sorry. That should be /0. Nope. Oh, I see what happened. Sorry. So what it's doing is it's actually passing the number to it. So I can't do that. So I need to just, that's the default behavior for that particular thing. So that should just, what am I doing? Hello, start link. This is what I do. Enum.map. Well, start link. This is going to kill me when I watch this on video. I'm going to be screaming at the TV. Yeah, you got to wrap me up. I'll be at the back. It'll be 30 seconds. Thank you, everyone. Thank you. What the hell am I doing now? Yeah, you can just cut the recording just before that. That'd be cool. Thanks.